So in this actually lecture, I thought to actually explain you the working of the pumps. So theoretically, I can explain that pump is just a, means providing the energy to the fluid actually. So in order to move it this elevation or position horizontally or any particular direction. So for that particular purpose, I downloaded some of the video lectures actually, and you can also go through on these various YouTube channels. These are the I found the most beautiful channels you have. So working of walls, you have two channels in that case. Then type of hydraulic pumps, then positive displacement pumps, centrifugal pumps. Again, another video on centrifugal pumps, types of centrifugal pumps, cavitation in pumps, and wall cavitation. So these are most important part in case of fluid machineries. So let's watch each videos one by one. So the first one, if you will see here,
Many different types of pumps exist to assist fluid movement in a variety of systems. An external gear pump uses two gears rotating against each other to provide fluid movement. One gear is driven by a motor connected to a shaft. This is called the drive gear because it is driven by a motor, and it in turn meshes with and drives the movement of the second gear. As the gears rotate away from each other and come out of mesh, they create an expanding volume on the inlet side of the pump. This creates a vacuum at the inlet port, allowing fluid to flow into the pump. Then fluid flows into the cavities and is trapped by the gear teeth. As the gears rotate, a flow path is created around the outside of each one. Fluid trapped in the slots between teeth is carried around and discharged into the cavity with the outlet port. Meshing of the teeth in the center of the pump seals the outlet port from the inlet port. No fluid passes between the gears. The advantages of external gear pumps are their high speed and pressure, relatively quiet operation, and that their design accommodates a wide variety of materials. Disadvantages include bushings in the liquid area can become worn and that they have fixed end clearances. Internal gear pumps are exceptionally versatile. This type of pump has one inner gear which is inside a second outer gear. The inner gear has a shaft driven by a motor and has teeth that protrude outward. The outer gear has teeth that protrude inward toward the center of the pump. As the inner gear rotates, it meshes with and moves the outer gear. Liquid is trapped in the gear spaces and carried from the inlet to the discharge. A stationary crescent-shaped divider separates the intake and discharge portions of the fluid. Advantages of internal gear pumps are a smooth and almost pulseless flow, and slightly more horsepower for its size. Disadvantages are its higher cost, limited size range, low to moderate pressure ratings, and few sources of manufacture. A rotary vane pump is a positive displacement pump that consists of vanes mounted to a rotor. The vanes are on an off-center drive shaft. As the shaft rotates, the variable length vanes slide in and out to maintain contact with the pump housing. The tension in the vanes is maintained by either springs or hydraulic pressure. As the vanes rotate, they create chambers of varying sizes within the pump. Fluid enters at the largest chamber. As the vanes rotate and retract, the chambers get smaller, forcing fluid to exit through the discharge port. The advantages of vane pumps are that they can handle low viscosity fluids at relatively higher pressures, can dry run for short periods, and develop a good vacuum. Their disadvantages include complexity and their unsuitability for both high pressure and high viscosity fluids. Piston pumps come in many different forms. A swash plate is a device used to translate the motion of a rotate shaft into the reciprocating motion of a piston. Swash plate piston pumps have a rotating shaft connected to a cylinder block containing pistons, which are pressed against a stationary swash plate that sits at an angle to the cylinder. As the shaft rotates, the pistons move against the swash plate, causing them to reciprocate within the piston block. The pistons create a vacuum that forces fluid in during half a revolution and expels fluid during the other half. On the intake stroke, a spring ensures the pistons pull back and maintain contact with the swash plate, causing fluid to fill the empty cavity left behind. On the discharge stroke, the angle of the swash plate forces the pistons back inside the piston block and discharges the fluid. The greater the slant on the swash plate, the further the pump pistons move and the more fluid they transfer. Piston pumps, in general, are manufactured with closer internal fits than other pumps. This means that internal slippage can be less, so that they operate with reasonable efficiency at pressures both too high or too low for the operation of other pumps. Radial pumps are designed so the pistons stroke in a direction at right angles to the shaft. The pistons are arranged like wheel spokes around a cylinder block with an eccentric central cam mounted on a drive shaft. As the shaft rotates, the cam moves towards the pistons, forcing them down into the cylinder block and discharging the fluid. As the cam moves away, springs help retract the piston and cause the intake stroke. Check valves ensure that fluid only enters the inlet ports and only exits the outlet ports. Radial piston pumps have a low noise level, very high loads at low speeds, and high efficiency. Hand pumps are used when a source of power is not available or where the extra expense of a power pump isn't warranted. For example, they are used on shop presses and other portable equipment, serve as standby pumps, and serve as sources of emergency power. Hand pumps are always of piston type and are usually constructed with a piston working between two check valves. Double-acting hand pumps are more efficient, allowing fluid to both enter and discharge on both strokes of the piston. Moving the pump handle in either direction allows fluid to be drawn in from the reservoir and discharged via the outlet ports. Check valves in all locations prevent fluid backflow.
Hi, I'm Adam. This is the Machine Tech video blog. And today I'd like to talk a little bit about the different types of positive displacement pumps. At first glance, there seem to be so many unique designs of positive displacement pump that it can be a little confusing. And it really wouldn't make a whole lot of sense to try and cover every single possibility in this one video. But what I have tried to do is to break it down into 9 basic mechanisms. At the heart of any pump, you'll find one of these mechanisms. I've also tried to show a real-world example of each different type of pump. Each basic mechanism falls within one of 2 categories based on what type of motion it utilizes. We have reciprocating and we have rotary. Reciprocating pumps are the first category. Every reciprocating pump utilizes some kind of expanding and contracting chamber and a series of check valves in order to draw fluid into the pump and then direct it out into the system. To illustrate this concept, let's take a look at pump number 1, the piston pump. The mechanism consists of a reciprocating piston inside of a cylinder with check valves at both the inlet and the outlet. When the piston is on its suction stroke, which is the upstroke in this case, the chamber inside of the cylinder expands. The pressure drops, the check valve on the suction side opens, and fluid is admitted through the inlet. By definition, check valves permit flow in one direction only, so they help to prevent backflow and direct the fluid through the pump. As the valve on the suction side of the pump opens, the valve on the discharge side closes. On the discharge stroke, which is the downstroke here, the piston pushes on the fluid in the cylinder. The pressure rises. The suction valve now closes, and the discharge valve opens to release fluid into the system. Here's an example of a common piston pump called an axial piston pump. This pump is a tad more complex than our little demonstration, but the pumping action is generated in exactly the same way. The axial piston pump has multiple pistons equally spaced on the end of a rotating angled plate. As the plate rotates, the pistons are driven into and out of their respective cylinders. You can clearly see the motion here. Like most reciprocating pumps, piston pumps are relatively efficient, and they're capable of generating very high pressures. Pump number 2 is the plunger pump. Plunger pumps look very similar to piston pumps, but they work a little differently. Unlike a tight-fitting piston, a plunger fits loosely in its cylinder. Just like when your bathtub overflows because you filled it too full with water before jumping in, the physical mass of the plunger alters the size of the chamber and displaces the fluid. This is a triplex plunger pump, which uses 3 staggered plungers for smoother flow delivery, but it is otherwise the same as our demonstration. Pump number 3 is the diaphragm pump. Unlike a piston or a plunger, an elastomer diaphragm is flexible. When it flexes, it changes the volume of the chamber, causing fluid to be drawn into or pushed out of the chamber. Our example is an air-powered double diaphragm pump. The pump is essentially 2 diaphragm pumps oriented back to back, with the diaphragms linked by a connecting rod, so it can pump on both strokes. One unique property of the diaphragm pump is that it doesn't require a seal, because the wet and dry sections of the pump are completely separated by the diaphragm itself. The second category of positive displacement pump is the rotary pump. All rotary pumps utilize some kind of a moving chamber that traps fluid and carries it from one side of the pump to the other side. To illustrate this concept, let's look at pump number 4, the gear pump. Actually, this configuration is more properly called an external gear pump. The mechanism consists of 2 rotating gears, one driving the other, inside of an oval housing. At the suction inlet, fluid is trapped in a chamber between the gear teeth and the inside wall of the housing. The rotary motion moves the chamber from one side of the housing to the other side, and as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet. Another configuration of the gear mechanism is the internal gear pump. In this type of pump, an outer gear in a circular housing drives an offset inner gear. The gears are separated by a crescent. Fluid is trapped in one of two moving chambers, between the inner gear and the crescent, or between the outer gear and the crescent. As with the external gear pump, the rotary motion moves the chamber from one side of the housing to the other side, and as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet. Pump number 5 is the lobe pump. Lobe pumps function very similarly to external gear pumps, but the rotors are driven independently by external timing gears. The rotors have 2 or more lobes, and the moving chamber is formed between the outer surfaces of the lobes and the inside wall of the oval housing. As the lobe rotates back toward the center of the housing, the tight clearance between the lobe and the other rotor closes the chamber and forces the fluid through the discharge outlet. Pump number 6 is the vane pump. A vane pump rotor has slots in it for sliding vanes. Centrifugal force flings the vanes out to contact the inside wall of the circular housing, forming a sealed chamber. Since the rotor is offset in the housing, the vanes extend and retract during rotation. The chamber increases in size at the suction inlet, drawing fluid in. At the discharge outlet, the chamber decreases in size, pushing fluid out. The nice thing about vane pumps is that they automatically compensate for wear because the vanes are constantly forced against the wall of the housing. Pump number 7 is the peristaltic pump. Peristaltic pumps contain fluid within a flexible hose. The hose is pinched between the rollers and the inside wall of the housing. As the rollers revolve around a center axis, they squeeze the fluid like a tube of toothpaste and move it through the housing to the discharge outlet. As with diaphragm pumps, peristaltic pumps do not require a seal because the fluid's completely contained inside the hose. They really excel at pumping high viscosity fluids with very large solids. I've even seen them pump whole cherries without significantly damaging them. Pump number 8 is the screw pump. Screw pumps can have a single shaft with large threads on it, but they usually have 2 or 3. The center shaft drives the other shafts like a screw or a worm gear. As the shafts rotate in the housing, fluid trapped in the gaps between the screw threads progresses along the length of the housing and is delivered to the discharge outlet. If you've ever seen an auger or a screw conveyor, this is pretty much the same thing. Our final pump is pump number 9, the progressive cavity pump. These bizarre little pumps may look somewhat like screw pumps, but they function differently. The rotor is shaped like a helix, and the housing is molded into the shape of a double helix. As the rotor rotates and oscillates inside of the housing, it forms a cavity which progresses along the length of the housing. Any fluid trapped in this progressing cavity is delivered to the discharge outlet. Well, there's your introduction to the various different mechanisms that make up the positive displacement pumps. And that's it for today from the Machine Tech video blog. Hope you learned something.
Centrifugal pumps are the most preferred pumping devices in the hydraulic world. In this video, we will have a conceptual overview of working of centrifugal pumps. At the heart of the system lies the It has got a series of curved vanes fitted inside shroud plates. The impeller is always immersed in water. When the impeller is made to rotate, it makes the fluid surrounding it also rotate. This imparts centrifugal force to water particles, and the water moves radially out. Since rotational mechanical energy is transferred to the fluid, At discharge sides of impeller, both pressure and kinetic energy of water will rise. At suction side, water is getting displaced, so a negative pressure will be induced at I. Such low pressure helps in sucking fresh water stream into the system again, and this process continues. This is the reason why priming is important for centrifugal pumps. If no water is present initially, the negative pressure developed by rotating air at eye of impeller will be negligibly small to suck fresh stream of water. Impeller is fitted inside a casing, so the water moving out will be collected inside it and will move in the same direction of rotation of impeller to the discharge nozzle. Here you can note one specialty of casing. It has got increasing area along the flow direction. Such increasing area will help in accommodating newly added water stream and will also help in reducing exit flow velocity. Reduction in flow velocity will result in increase in static pressure, which is required to overcome resistance of pumping system. Here you can see more details of vanes inside impeller. They are backward curved vanes with state-of-the-art eye configuration. This vane is extracted from a Kirloskar pump model. If pressure at suction side of impeller goes below vapor pressure of water, a dangerous phenomenon could happen. Water will start to boil, forming vapor bubbles and spoil impeller materials over time. This phenomenon is known as cavitation. More the suction head, lesser should be the pressure at suction side to lift water. This fact puts a limit to maximum suction head a pump can have. Careful pump selection is required to avoid problem of cavitation. Current impeller type is enclosed. Semi-open and open impellers are also in use depending upon application. If the working fluid is cloggy in nature, it is preferred to use open kind of impeller, but they are slightly less efficient. Mechanical design of centrifugal pump is always challenging. A shaft is used to connect between the impeller and motor. Since water pressure inside casing is huge, a proper sealing arrangement is imperative in arresting water leakage through shaft casing clearance. Mechanical seal or stuffing box-based mechanism is used for this purpose. Impeller is mounted on bearings, but at suction side of impeller, it is not advisable to fit a bearing since it will block the flow. So bearings have to be fitted at the other end. This means impeller is mounted like a cantilever. For high flow rate pumps, a bearing housing with cooling oil is necessary for improving life of bearings. We thank Kirloskar Brothers for their technical support and creation of this video.
Hi, I'm Adam. This is the Machine Tech video blog to talk to you a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? how much power is required to run it. But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed. The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint caps, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. And if the vanes are sandwiched between 2 shrouds, then it's a closed impeller. Closed impellers are more efficient than either semi-closed or open impellers because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump, it's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on one end of the shaft and the bearings are offset to the other side. This configuration places the suction and discharge piping at 90 degrees to one another, with the inlet directly in front of the suction eye at the center of the impeller. This is why pumps with overhung impellers are more commonly referred to as end suction pumps. End suction pumps are abundant in industry because they're relatively cheap and easy to manufacture, but they do have one big disadvantage arising from the way that fluid travels through the pump. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does supporting the impeller with bearings on both sides generally improve shaft support, it also means that many of these pumps can employ symmetrical closed impellers with double suction. Since there are identical low and high pressure zones on both sides of the impeller, this effectively eliminates thrust forces due to pressure imbalance. And this design has another key advantage. The suction and discharge piping are normally positioned parallel to one another on opposite sides of the pump, and the casing is split axially so that just by removing some bolts and pulling the cover off, maintenance technicians can access the rotating assembly inside the pump without removing the whole pump from the system. This axially split design is why pumps with impellers between bearings are more commonly referred to as split-case pumps. Now, those are all pretty convincing reasons to go run out and get yourself a split-case pump right now, but of course there has to be a disadvantage. Because the manufacturing processes and the sealing requirements for split-case pumps are much more elaborate than for end suction pumps, they're also naturally more expensive. Next on the list of design elements is orientation, either horizontal or vertical relative to the pump shaft. Centrifugal pumps are usually oriented horizontally, but they can also be oriented vertically. Vertical pumps are used in plants where a reduced footprint and space savings are desirable. And you may also find one down at the bottom of a well or sump connected through a long line shaft to the driver above. This brings us to the mounting method of the driver, usually an electric motor. There are two options for transmitting rotational force from the driver to the pump, either frame mounted or close coupled. If the pump and driver are two separate units, as they are here, then the pump and driver shafts will need to be connected by some type of a coupling. Now, couplings come in all shapes, sizes, and styles, but one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed. To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame mounted. For large, heavy equipment and for all split-case pumps, frame mounting is really the only way to go. A second option is the close-coupled mounting method, in which the pump and its driver share a common shaft, with the impeller mounted overhung on one side of the driver shaft. In this case, there is no need for a coupling or any of the extra labor required to perform sensitive alignment procedures. However, since both the pump components and the driver components are supported on the same shaft just by the bearings in the driver, this mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth, until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal pumps: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. And that's it for today from the Machine Tech video blog. I hope you learned something. Hi, I'm Adam. This is the Machine Tech video blog, and today I'd like to talk a little bit about centrifugal pumps. Centrifugal pumps are definitely one of the most common machines in the industrial landscape. In fact, they're second in number only to electric motors. And when you consider that electric motors are used to drive centrifugal pumps, it's safe to say that the lion's share of energy usage in the world goes towards pumping fluids with centrifugal pumps. So if you're an industrial maintenance technician, mechanic, machinist, you'll come across these machines at some point in your career, so it will do you some good to know how they work in the first place. In general, A pump is a machine which converts mechanical energy into the kinetic energy of a pumped fluid for the purpose of transporting that fluid from one point to another. But in order to be classified as a centrifugal pump, a pump needs to have two unique components. The first is a rotating disc with curved blade-like veins on it, called an impeller. And the second is a specially shaped pipe called a volute casing, which contains the impeller and the pump fluid. In the most basic sense, here's how a centrifugal pump works. Fluid enters the pump at the center of the impeller, called the suction eye. Friction between the fluid and the surface of the rotating impeller causes the fluid to rotate. Think about it like this. Just like the friction between the road and the rubber in your tires propels your car forward, the impeller gains traction on the fluid as it spins in contact with it. The rotating fluid is thrown to the outside of the impeller by centrifugal force, a phenomenon which causes objects revolving around a center point to move away from the center. This is how the fluid picks up kinetic energy from the impeller, and this method of energy transfer by centrifugal force is why these pumps are called centrifugal pumps. The amount of energy actually added to the fluid is dependent on three factors: the density of the fluid itself, the impeller's speed of rotation, and the impeller's diameter. From the impeller, the fluid is released into the chamber of the volute casing and directed around to the discharge outlet, and ultimately into the system. Let me take a minute to set the record straight. A very, very common misconception is that these curved veins help to move fluid by cupping it and pushing it through the pump. So then the correct direction of rotation for this impeller would be clockwise, right? Well, that's not really what the veins are there for. The veins' purpose is to conduct the fluid along the smoothest possible path as it travels through the pump. Backwards curved veins help to stabilize flow conditions at high speeds and reduce demands on the motor. The correct rotation for this impeller is actually counterclockwise. And you can always tell the correct direction of rotation of an impeller just by looking at the way that the veins are curved. It's important to add that because of the way that centrifugal pumps impart energy to fluid, the impeller must always be fully submerged and in direct contact with the pumped fluid. As we can see from this little light-duty pump, a centrifugal pump will not pump air, and it will not suck fluid through piping like a straw. So before the pump is turned on, the casing must be flooded with fluid, a process known as priming. And during operation, there must be a sufficient amount of available fluid under positive pressure at the suction inlet of the pump to replace the fluid which is being discharged. This is usually accomplished by placing the pump below the fluid level of the source tank. If the pump is ever starved of fluid, certainly the pump's performance will be affected, but it's actually more serious than that. It's possible that the pressure at the suction eye of the impeller will drop below the vapor pressure of the pumped fluid. If that happens, then the fluid will effectively boil. Little bubbles will form, travel partway through the impeller, and then collapse at supersonic speeds like little bullets, taking bits of the impeller along with it. This is a condition known as cavitation, and a pump that's experiencing cavitation is not long for this world. I know that I use these little water bubbles in my animations to illustrate the fluid path through the pump, but actually, that kind of entrained air or any other gas is the worst case scenario for a centrifugal pump. Let's talk about the volute casing. Volute refers to the shape of the casing. A volute is a geometric shape defined as a spiral with an ever-increasing radius, like a snail shell. Hopefully you'll notice that the volute chamber on this pump doesn't stay the same size all the way around. It actually increases in area closer to the discharge outlet. And at the point where the discharge outlet begins and the volute chamber sort of starts over, there's a wedge-like protrusion called the cutwater. The cutwater physically separates the discharge outlet and the volute chamber, and it ensures that fluid actually leaves the pump instead of just recirculating over and over again inside of the volute chamber. Now, the increasing area of the volute chamber is essential to the function of the pump because that's how the pump develops pressure. We've talked about how the impeller imparts kinetic energy to the pumped fluid. And when I say kinetic energy, think of it as the speed of the fluid flowing through the pump. But flow speed is only half the equation. A pump also needs to be able to develop sufficient pressure to meet the requirements of the system. Usually this involves overcoming gravity by raising fluid from a lower elevation to a higher elevation, and overcoming the resistance or friction of the pipes which conduct the fluid. Think of pressure as the ability to accomplish a task, and flow speed as how quickly the task can be accomplished. To build pressure, the pump has to do some science magic to convert kinetic energy into pressure energy. As fluid travels through the volute chamber, it actually starts to slow down as the area of the volute chamber increases. That's because flow rate, or the amount of fluid which is moved during a given length of time, is dependent on two factors. One is the speed of the fluid, and the other is the size of the chamber through which it's moving, meaning how much of the fluid is moving at that speed. If the flow rate is constant, then an increase in the size of the chamber would result in a corresponding decrease in the speed of the fluid. This is where a guy by the name of Daniel Bernoulli comes in. He discovered 300 years ago that there's an inverse relationship between a fluid's velocity, or speed, and its pressure. Meaning that if the velocity goes up, then the pressure comes down. And if the velocity goes down, then the pressure automatically goes up. So as the fluid is slowing down in the ever-expanding volute chamber, it's also picking up pressure. So that by the time the fluid reaches the discharge outlet, a great deal of its kinetic energy has been transformed into pressure energy. And I think that's a pretty amazing little trick. Well, there's your introduction to centrifugal pumps, their function, the main parts, and the basic theory of how they work. Pumps and pumping are rich and complex topics, and we'll definitely be coming back to them in later videos. But for now, that's it from the Machine Tech video blog. Hope you learned something.
Those of us that are familiar with self-priming centrifugal pumps, we know that we must first fill the volute with water. We can now start the pump and watch what actually occurs inside of the pump during priming. After we fill the volute casing with water and we energize the pump, the impeller turns in a counterclockwise rotation. The initial prime of the pump is slung through the volute scroll, or the ever-increasing water channel, into a pressure cavity or a discharge chamber inside the volute. Inside this discharge chamber, the air and water separate.
Hi, I'm Adam.
The heavy
This
water
is the
falls
Machine
back
Tech video
down through a
blog.
recirculation
Today I'd like to
port,
talk a little bit.
and the air then is evacuated through an open-ended line or through an air release device. All the while that we recirculate the water inside the casing and remove the air from the top, we create a low pressure at the eye of this impeller. Due to differential in pressure, atmospheric pressure that we live around every day is higher than the lower pressure created at the eye of this impeller. Due to that differential in pressure, atmospheric pressure outside begins to force liquid up the suction pipe. As liquid moves up the suction pipe, it pushes all the air ahead of it into the volute casing, where it is handled through the recirculation process. Again, the air is handled off the top, and the heavy water recirculates back down into the volute scroll area. I'll close this valve right now and create a suction line capable of pulling a vacuum. Ahead of it moves the air, pushes it into, handles it through the recirculation process, and once the water arrives, the pump then Metal erosion is a costly problem. It attacks pumps, valves, piping, and other expensive equipment. No matter what type of liquid is being used, there's always the risk of damage from flashing and cavitation. Wherever there's a restriction in flow, the decrease in pressure can cause a fluid to reach its vapor point. Flashing occurs when the fluid vaporizes and remains a vapor. Metal erosion caused by flashing appears smooth and shiny. Cavitation occurs when the fluid vaporizes, then returns to a liquid state as the pressure increases downline. The metal damage caused by cavitation is rough and irregular due to pitting of the surface. Cavitation is a major source of damage in control valves and other components. Cavitation occurs as a liquid passes through a restriction, such as a valve. The restriction causes the liquid's velocity to increase and its pressure to decrease. The point of maximum velocity and minimum pressure is called the vena contracta. Vapor bubbles form in the liquid when the pressure falls to near the level of the liquid's vapor pressure. When the pressure recovers downstream, the vapor bubbles implode and return to liquid form. After the initial bubble formation and collapse, the bubble may reform and collapse a second time. Liquid microjets form when the recovering pressure makes an indentation in a bubble. Then the microjet bursts through the bubble. These implosions can also cause local pressure waves of up to 100,000 pounds per square inch. The combination of pressure waves and microjets can cause severe damage to the valve plug, seat, and body when they're located near the material surface. Cavitation can also cause unacceptable noise and vibration that reduce efficiency or lead to loss of process control. Even though cavitation occurs, it doesn't always cause damage. The extent of cavitation damage is affected by the following factors: the intensity of the cavitation. Greater drops in pressure increase the potential for damage. The materials used in the construction of the area where the cavitation occurs. Hardened materials reduce damage. The length of exposure to cavitation. The more frequently that cavitation occurs in an area, the more likely it is to sustain damage. Valve size. Increasing the valve size tends to make the effects of cavitation worse. The design of the valve and trim in the area of cavitation. High recovery ball and butterfly valves are more susceptible to cavitation damage. If there is leakage occurring when a valve is closed. Fluid leakage moves fluid from a high pressure area to a low pressure area, which results in cavitation and potential damage. Cavitation damage can be reduced by altering or accommodating any of these factors. Cavitation damage can often be reduced or prevented by using the proper components. Emerson offers these solutions. Valve liners are constructed of hardened materials to protect the valve body. Pressure staging keeps the pressure from falling to near a liquid's vapor pressure, which helps prevent vapor bubbles from forming. Pressure drops are staged by the use of expanding nozzles or expanding flow areas. For example, in the Cavitrol 3 valve trim, nozzles have holes shaped to manage flow separation. Multiple small holes shift the noise to higher frequencies. Cavitation is isolated by directing fluid into the center of the valve using a flow-down orientation so bubbles implode away from the valve components. In addition, the Cavitrol 4 valve trim has expanding flow areas that decrease pressure as the fluid flows through, limits changes in pressure at each step to prevent fluid from reaching the vaporization point, and prevents leakage. Fisher Control Valve Technology from Emerson Process Management provides customers around the world with leading critical valve solutions. You can count on Fisher Products, backed by its 125 years of valve development and manufacturing experience, to solve your critical valve needs.
So in this actually we have seen various type of valves, centrifugal valves and priming and cavitations, and how these actually cavitation creates the serious problems for this damage of the walls, and let's say the cavitations in the walls. So with this actually we can end this session.